Now we are going to discuss about aquifer properties. These properties are required for the groundwater hydrology, that are porosity, specific yield, specific retention, coefficient of permeability, transmissibility, storage coefficient and specific storage. Porosity. Porosity is the ratio of volume of voids in the soil mass to the total volume. Generally, it is expressed as a percentage. Here, the volume of voids in the soil mass is denoted by VV, and total volume is denoted by V, and also the porosity is denoted by N. Porosity N equal to volume of voids divided by total volume into 100, because this is expressed as percentage. Porosity is measure of the water holding capacity of the soil mass. If the porosity is high, that means it indicates that the water holding capacity of a particular soil is also high. Porosity is depends upon the size and shape of the particle and compaction of the particle. In generally, the porosity is varies from 30 to 55%. That is varies different from soil to soil or type of material to material. Specific yield. Specific yield is the ratio of volume of water that is extracted from the aquifer to the total volume of the saturated aquifer. Here, saturated aquifer means is the, in case of unconfined aquifer, that is from the water table to the bottom surface, this is the saturated zone. Whereas in case of confined, that is from the piezometric surface to the bottom layer. So this is the ratio of volume of water extracted from the aquifer to the total volume. Here the volume of water extracted from the aquifer is denoted by VW and the total volume is V, and the specific yield is denoted by this is the symbol SY. Then the specific yield is equal to VW divided by V into 100. This is also expressed as the percentage. Here we are going to note one point, that is the all quantity of water stored in the soil mass is not simply drained out by gravity, because some quantity of water stored in the soil mass because of their molecular and specific surface tension forces. Next one is the specific retention. Is the also volume of water that is retained in the soil mass to the total volume is nothing but specific retention. That means a part of water is stored in the soil mass because of their molecular and specific tension forces. That retained water in the soil mass to the total volume is nothing but specific retention. This is also expressed as percentage. Here SR is equal to specific retention is equal to volume of water retained in the soil mass denoted by VR divided by total volume V. This is also expressed as percentage because this is the formula for the estimation of specific retention. Here one more point, based on these three definitions, porosity, specific yield and specific retention, we are going to give some relation between these three. So earlier, volume of porosity is the definition, refers that volume of voids to the total volume. Volume of voids is nothing but volume of water retained from the aquifer and volume of water passing through the aquifer, two parts. Volume of water passing through the aquifer denoted by VW, and the volume of water retained in the aquifer it is denoted by VR. That means VV equal to VR plus VW. So that this V here, this is the formula. Here instead of VV equal to VW plus VR, right here the definition of volume voids ratio is nothing but volume of voids to the total volume. So here VV divided by V and also divided by V this side, that means both sides divided by V, we have the equation. This is volume of voids divided by total volume is nothing but porosity, and volume of water divided by V, that indicates that volume of water divided by V is nothing but specific yield, and also volume of water retained in the soil mass VR divided by total volume indicates the specific retention. Here, based on this one, porosity equal to specific yield plus specific retention. Right here, porosity is sum of specific yield and specific retention. Right, it should be noted that it is necessary that the soil which is high porosity will not have high permeable, because high porosity soils are not transfer water high quantity, because the transfer of water from soil media to out, that is depends upon the permeability of the soil. Some cases the porosity is high, but the water released from the soil mass is low because of the low permeable soils. For example, clay having high porosity value but having less permeable. Because of that property, clay is specific retention is very low, that is around 3 to 4%. Whereas in case of sand, that also having high permeable and also having high porous, but the specific yield is too high, that is around 25%. So these are the values here: sand, gravel and sand, sandstone, clay, limestone, shale and granite. Here sand having specific yield is equal to 25%. Here the porosity is 35%. So if the porosity is more and also a specific yield is also more. But whereas in case of clay, here the porosity is 45%, but the specific yield is very less, that is 3%, because the coefficient of permeability is very low, that is 5.0 into 10 power minus 9, whereas in case of sand 5.0 into 10 power minus 4. So the specific yield is mainly depends on the coefficient of permeability, not depends on the porosity. So these are the values for gravel. In case of gravel, the specific yield is 22% and the porosity is equal to 25%. In case of gravel and sand, the specific yield is 60% and porosity is equal to 20%. So here what we have to understood, that the flow rate from the soil is mainly depends upon the coefficient of permeability, not depends on porosity of the soil mass. Then coefficient of permeability, it refers the flow of water from the soil mass. If the flow of water is too high, that indicates that coefficient of permeability is high. Here, and also the coefficient of permeability is equal to the discharge per unit area. That means discharge per unit area means therefore coefficient of permeability units equal to velocity. Because discharge per unit area means discharge equal to meter cube per unit area meter, then we have meter per second. Coefficient of permeability is the flow rate of a soil mass. It refers the flow rate of the soil mass. The coefficient of permeability is equal to the discharge per unit area. Discharge per unit area means is nothing but velocity. Therefore, the units of coefficient of permeability is equal to the velocity units, that is meter per second. The coefficient of permeability is also called hydraulic conductivity. And next property is the transmissibility. Transmissibility is the discharge rate per unit width of an aquifer at a unit hydraulic gradient. Therefore, here the transmissibility is equal to K. K is nothing but velocity. Per unit width means only B. This is the depth of an aquifer. In case of unconfined aquifer, this B refers the water table to the bottom, whereas in case of confined aquifer, this B refers that is the thickness between the between two impervious layers. Transmissibility is usually expressed as meter square per second. Generally, the transmissibility values varies in between 1 into 10 power minus 10 power 4 and 1 into 10 power 6. In generally, this is in between the 1 into 10 power 5 liters per day per meter. And next property is storage coefficient. Storage coefficient is the volume of water that is released from the prism of unit cross-sectional area as the water table drops by unit. Right here, this is the diagram. So this is the unit drop, this is the unit, this is the cross-sectional area. This is in case of unconfined aquifer, because this is the one impervious layer, this is the another impervious layer, this is the piezometric surface. In case of piezometric surface, by pumping is started, then the water drops per unit depth. And we know the cross-sectional area, this one. Whereas in case of unconfined aquifer, this is the unconfined aquifer, this is the impervious layer, this is the water table, then drops water by 1 meter or unit. Then this is in case of unconfined, in case of confined aquifer. Storage coefficient is also nothing but, this is also nothing but water extracted from the aquifer to the original value. Right, this is also in case of confined aquifers, so storage coefficient is also equal to the, almost all equal to the specific yield. Darcy's law, 1956, Darcy have given one law for the velocity of flow through the porous medium. According to Darcy's, the velocity of flow through the soil is proportional to the hydraulic gradient. Here V is equal to K into I, where K is the coefficient of permeability and I is the hydraulic gradient. Hydraulic gradient is the head loss per unit length. Here there is no units for the hydraulic gradient. Therefore, the units of coefficient of permeability is equal to the velocity units. And here this velocity is known as apparent velocity or discharge velocity. Why? Because velocity equal to Q by A. This is standard formula where Q is equal to discharge from the aquifer. A is the gross cross-sectional area. Here the gross cross-sectional area indicates that a part of porous media there and also part of solids also there. Here, because the water can flow only through the porous media and not through the particles, because this is, strictly speaking, this is not actual velocity. So this actual velocity is different from this apparent velocity. Therefore, the actual velocity through the porous is called the seepage velocity, right? So here for the determination of actual velocity equal to apparent velocity, we know, divided by porosity. If the porosity is equal to 100%, this actual velocity or seepage velocity is equal to, almost all equal to apparent velocity or discharge velocity. If the porosity is 50%, actual velocity is different from the apparent velocity, or seepage velocity is different from the apparent velocity, right? Here that the actual velocity or seepage velocity is depends upon the porosity of the soil mass. And as it is difficult to measure the seepage velocity in case of groundwater hydrology, so that in generally we are going to take, unless otherwise specified, we are going to take apparent velocity for the groundwater hydrology calculations. Here you see the one diagram. This is the soil mass length equal to L. The water flows from this direction to this direction. Here this is the one piezometer installed here and another piezometer installed here. The water at the upstream side is raises up to this point, whereas in case of downstream side piezometer, the water level is raised up to this point. Have some difference. This point to this point is known as, this is known as the head loss. This is the length of the specimen. Therefore, and also here some notations are given here. This is the center of the specimen to the bottom is nothing but head, that is the datum head, and also here having the water level raises up to this point, this is known as pressure head. Here datum head plus pressure head, because there is no velocity, because this is very less. Here downstream side also one is datum head, center of the specimen to the bottom, and also pressure head here denoted up to this one, this is the pressure head. Therefore, for the calculation of hydraulic gradient, I equal to delta H divided by L. This is the formula for the determination of hydraulic gradient. And next one, validity of Darcy's law. Generally in soil mass in an aquifer, the flow is laminar. Suppose the flow is laminar, the Darcy's law, the upper limit of the Darcy's law should be equal to Reynolds number is unit. That means you know the formula for the determination of Reynolds number, Rv is equal to rho Vd by nu, where rho is the mass density of the fluid. V is the velocity of flow, D is the particle size, that is the effective particle size, that is denoted by D10 size, whereas mu is the viscosity of the fluid, and this is the formula for the determination of Reynolds number. If the Reynolds number is unit, then the laminar flow exists. In some cases, this in case of aquifers, the flow is allowed, the Reynolds number is up to 10, but in case of gravel and sand rocky fields, the Reynolds number is more than 10. At that particular cases, there is no applicable of the Darcy's law. The analysis is carried out first analyzed by Dupuit in 1863 and later modified by Thiem in 1906. In their analysis, in their theory, they have given some assumptions and some important points for the extraction of water from the confined aquifer as well as unconfined aquifer. Here they have given some important assumptions. The aquifer is homogeneous and isotropic and uniform thickness. The aquifer has an infinity lateral extent. The well fully penetrates the aquifer and receives water from the entire thickness. The flow is laminar, linear and radial. The flow is horizontal and uniformly distributed in the vertical direction along the thickness of the aquifer. And also they have considered flow is laminar and Darcy's law is applicable. So before going to derive the formula for the extraction of water from the confined aquifer or in case of unconfined aquifer, we are going to learn some definitions. Here, before pumping is started, the water level in the well is stationary. That means in case of unconfined aquifer, the water level refers to the water table in the aquifer. Whereas in case of confined aquifer, the water level in the well refers the piezometric surface of the aquifer. As the pumping is started, the water level in the well drops, the radial flow occurs into that well, and the water table in that well is assumed that it is the inverted cone as the pumping is continued. As the pumping is continued, initially this is the water level. Initially this is the water level in the well. Once the pumping is started, the water level is drawn down like this, and the radial flow enters into the from both sides. This is one side, this is the another side. From both sides, the radial flow enters into the well, and then this is the groundwater table. This is the initially groundwater table is horizontal. After pumping is started, the water drops from this point to this point. This is known as drawdown. Once we have drawdown from this point to this point, the water table also changes like this. This is like inverted cone around the well if the pumping is continued. This inverted cone, this cone is nothing but cone of depression. That influenced area around the cone is known as area of influence. The area of this cone is known as radius of influence. And then when the rate of pumping is kept constant, initially the drawdown curve gradually changes with time. This phase is called the unsteady flow. However, the pumping is continued for a long time. The equilibrium stage is reached when the cone of depression is stationary. At this stage, the cone of depression is stationary. At this stage, the quantity of water entering into the well is equal to the water extracted from the well by pumping. Right? Where that reaches the equilibrium stage indicates that the inflow is equal to the outflow.